Oops. Hello, everyone. So I'm Maxime Varese, PhD student at AIM. And so today I'll speak about the neutral gas heating in a low metallicity environment. So first of all, what are we interested in knowing how the neutral gas is heated? Okay. So as you know, the star formation occurs mainly from cold molecular clouds. But in order to sustain star formation over quite long time scale, you need to take some atomic gas and cool it down to a molecular state. And so if you have some way to heat your atomic gas, then you have a regulation mechanism for a star formation that is effective over a quite long time scale. And you have some different ways to heat this atomic gas. So either by ionizing hydrogen or photoelectric effect on dust grains and also shocks and turbulence that can hit the gas. But in this study, we consider only stellar feedback, so hydrogen ionization and photoelectric effect. And also, it's important to understand how it's heated because we observe mainly cooling lines from the neutral gas, so C2, O1, and these lines are formed because the gas is heated. And we use them for star formation diagnostic and heating efficiency diagnostic. And so it's quite interesting to understand really how these lines are formed. So a quick view of how the gas is heated. So you have some kind of energy input, which can be a cosmic ray, or photons, which range from optical to X-ray in energy. And it will hit something in your interstellar medium, so a dust grain or an hydrogen atom. In both cases, it will release an electron, which will collide with hydrogen atom, and so you heat the gas. And then you cool down the gas, and you have a thermal equilibrium. And what we observed are these cooling lines, so mainly C2 at 158 microns and O1 at 63 microns. And what we would like to do is going all the way back from these cooling lines to the local physical mechanisms that can heat the gas. So in the Milky Way, there's a lot of dust because it's high metallicity. And so we know that the photoelectric effect dominates the heating. But when you decrease the metallicity of your gas, you also decrease the dust to gas mass ratio. And so you don't have a lot of dust anymore. And something else could take the place of photoelectric effect to heat your gas. And this was investigated by a paper from Bialy and Sternberg, 2019. So you have density and metallicity of the gas, and in high metallicity, photoelectric effect dominates, and below 1/10 solar metallicity, it's the cosmic rays. But this study is still theoretical, and it doesn't take into account the X-rays. And we know that in low metallicity galaxies, the X-ray luminosity increases by a factor of 6. So it's given in this paper of Lemer et al. But we have some more recent papers that claim that it can be even higher, so more than 1 order of magnitudes higher in low metallicity galaxies. And so what we would like to know is whether the X-ray can become a significant source of heating in this low metallicity environment. And so to investigate that, we use the dwarf galaxy survey, which is a sample of local star-forming dwarf galaxies, which has a huge range in metallicity from 135 solar to 1/2 solar. So we will be able to study the variation of heating with metallicity. And it has been observed in the infrared spectroscopy by Spitzer and Herschel. So we have access to these cooling lines. And interestingly, we also have X-ray observations with some ultraluminous X-ray sources that are detected in 11 galaxies. And so we will, at the end, use this X-ray luminosity and as a validation of our models. And also, what is quite interesting about this sample is that the DGS galaxies lies at the transition between the photoelectric effect dominated heating and cosmic ray dominated heating in the Bialy and Sternberg study. And so we hope to be able to see this transition in the data. Okay, so I will explain quickly the modeling method that we use. So we don't have a spatial resolution in the DGS galaxy. It's only integrated spectrum. And so it would be logical to use one-dimensional radiative models to model the galaxies. This is what we do. So we have models with a central source, which is a stellar cluster, and an X-ray source that we can remove if we want to see the impact of X-rays specifically. And the surrounding gas has a given density, metallicity, and depth that we can vary. But only one-dimensional model is probably not enough to account for all the structure of the ISM. And so we model the galaxies as a collections of one-dimensional models with a few hundreds of different models. And in order not to have too much free parameters, we tie these models with statistical distribution. So we can have a statistical distribution on density, ionization parameter, metallicity, whatever we want. And this allows us to have only 15 free parameters in the model with still hundreds of different models. So quite a complex modeling. And so, as you can see, you have a scheme of a galaxy, and each model has its own physical parameter in its own simulated spectrum. And then we add all the spectrum to get the integrated spectrum that we will compare to the observation. And the best combination of model is found with the multi-Rhys-code, which uses MCMC techniques, and with the star-forming galaxy with X-ray sources grid of model, which is based on cloudy. So now that we have the modeling method, sorry, I will go through all the three different mechanisms of heating, which are first photoelectric effect. So you have metallicity here and the contribution of photoelectric effect to the atomic gas heating. And so you can see that at high metallicity, the photoelectric effect actually dominates the heating, which was expected, but it's a nice way to validate the model to find this. And when you decrease the metallicity, the photoelectric effect decreases as well, down to around 20% for the lowest metallicity galaxies. So something else takes the place of dust, indeed. And can it be X-rays? So you have here the photoionization that is by X-rays and also a bit of UV photons. And what was surprising is that it accounts for a significant amount of heating, even in the higher metallicity galaxies. So you have one galaxy here, which has 40% of X-ray heating. And when you decrease the metallicity, you have some galaxies here with an X-ray heating fraction of around 30%. So it is actually a significant source of heating. And for the cosmic rays, in high metallicity, there doesn't account for a lot of heating. And when you decrease the metallicity, you have more cosmic ray heating, which was again expected. So nothing new here. But this is to be taken carefully because we probably overestimated the cosmic ray ionization rate in the models. So if it's the case, it would mean that the cosmic ray heating is actually lower and the X-ray heating is actually higher. That's what we found here. You have the general picture here with all the three mechanisms. And the main message is that X-ray heating from stellar objects can provide a significant source of feedback at a galactic scale. And so it's important to take them into account in neutral gas modeling or simulations. So once we have these results, we can wonder what can we actually do with that. So first, we had a look on the pH heating efficiency, because in the Milky Way, so I told you that the dust dominates the heating, and the dust heating is dominated by pHs. And we have an observational proxy to estimate the pH heating efficiency, which depends on the pH luminosity, C2 luminosity, and O1 luminosity. And when you apply it to the DGS galaxy, you find that in some galaxies, we have a value for this epsilon pH that is higher than the maximum theoretical value that was predicted by Tilens et al. And so this can seem to be a problem, but actually it's not, because the C2 plus O1 luminosity accounts for all the heating and not only the dust heating. And we want to correct this factor, so using a corrected epsilon pH with this fraction of photoelectric heating that we computed just before. And when we do that, we find that for all the galaxies, we now get values that are compatible with theoretical expectation. So it's kind of nice. And if you want some more information on photoelectric effect efficiency, you can check Leo Belloir's poster, which is on this topic. And one last thing that we wanted to try is, well, the models have an X-ray sources in it, and the luminosity of these X-ray sources can be varied. And so can we predict the X-ray luminosity of the galaxies? If it's the case, it would be nice because we would have a way to have insight on X-ray properties of galaxies with only infrared observations. And this was proposed for AGNs first. So if you have high ionization potential lines, you should be able to have information on the X-ray ECD shape. So it's from this paper from Khan et al. 2019. We wanted to try that because we have high ionization potential lines. We actually have only one, which is O4 at 26 micron. And when we do it, so you have here the observation that I mentioned in the beginning in X-rays, and the luminosity that we predict here. And it works surprisingly well with a lot of uncertainties, but we can reproduce the X-ray luminosity. And yes, there's still a lot of uncertainties, and that's because the O4 line is not very high ionization potential. To have better results, we probably would need higher ionization potential lines, so neon 5 or highly ionized silicium, which should be observable with JWST. So maybe someday we'll have observation and we will have some better way to look at these X-ray sources. But still, even with only one line, we have information on X-ray sources that we don't see. We don't need to have X-ray observation to have this measurement here, so it's pretty nice. Okay, so here are my conclusion and perspective. So mainly, I just like to mention the Prima mission, which will may provide, if it's selected, some great data in infrared. And so it will allow us to study both the ISM and the X-ray properties of galaxies with only one mission. So thank you for your attention, and if you have questions, I'll try to answer.